Hello everyone. How are you today? It's Tuesday and empty. Okay, so the cryptography, I think this is one of the difficult module in this course. I'm trying to my best to assist you to solve the module and the familiar with that the basic concept of the cryptography. In the last class, I think we have some not enough time to describe some pawn tools, the pawn library. So let's study how to use the pawn library in Python and how to interact with the process. So that is the very critical to solve the module the challenges. Okay, so I will start again the level 2 and the workspace. So here, let's see the challenges and run. So in the module 2, we have to uh, the decrypt the secret encrypt with one-time pad algorithm. Through this, the most secure encryption mechanism, if you could just securely transfer the key. So one-time pad, what kinds of operations are used? So XOR between the keys and the plain text. We can get the ciphertext, right? In reverse process to decrypt the ciphertext, we just, yeah, the XOR, one more XOR operations, they give us the plain text. So that's the reason why we use the XOR operation in this the one-time pad. So here, as you can see, they provide the keys, right? Already, the base 64 based the code, okay, and also they give us cipher text, right? That means based on these two-factor key and ciphertext, we can get what? Yeah, input the plain text. How to do that? We have to XOR between these two factors, the keys and the secret. So presumably the lengths of these two factors probably presumably the same, right? So that makes uh, the exact plain text. So in order to that, we can take this input value by interacting with process. How can you do that? So now let's do that. Um, okay, here I just make the new Python files names. So one time pad, and now we can put some code here. So we need to import the library form first to use the process function, right? Import and process. Okay. Okay. Let's everything and use the P. This is gonna be the start the process. What our run challenges. Okay. So from this P, we can get some data. Um, okay, skip this. I think that we did this. So P again can have a method from process functions. So P, the read until method. What we can give some conditions here. What conditions? So you can see Chillin's run. Oh, yes. Now we are trying to take this key, right? What does it mean? What does it mean? These two equal symbols. So it means the padding. So the base 64 have to be a multiple of 4. So to align the multiple of 4 or 16, this means there's a padding. Okay, and so we will take these key values and the ciphertext. So we like to this line values. So we have to put the conditions this text and paste. Yes, in this way you can get this value. Uh, and then we can decode key P64 64 P method is P read line, okay, and decode the key based on base 64 P64 decode what key 60 P64. Okay, let's print. The first key is a key P64. Right, and another one print key, the decode key. Okay, so let's run this code. You can see, okay, and one time. CD, okay, Python, okay. Okay, so here, so we got the key basis 16 full, right? This is the key, and the yeah, this is the key, and this is the decoding key in hex, right? So can you see some characters like 0C0, not 0, it is O. So what's the meaning of this? So hexadecimal, the prefix is a slash, maybe with slash, so X, right? And two letters should be hex, but in this case, the 0C0, what's the meaning? What's the why it has three letters after hex prefix? Anyone knows? Cyber chat. You know the this site website Cybershake. So very uh, useful for the cryptography thing. So you can see we can decode some base encoded code with base 16.4. So here let's decode. Yes, this and make this hex. Oh, sorry. Base 16.4. Yes. So in this case, this is that correct? UG. So this decoded code, encoded code, decoded by the base 16.4 decoded functions, and then convert to the hex value, hex byte. Here, the 6457, right? Can be so B A and 0C. No. So what's this hex? E. Sure. So uh, this code can be decoded and converted to the hex key here. So you can see like this O or this C. This is the correct, but yes, this character so like capital I, or you can see these symbols. So hex value has only the five character A, 2, F, A, B, C, D, E, F, 6 characters, right? So non-literal character, non-literal character cannot be displayed in hex mode. So that's the reason. So we have to convert this character in ASCII, the code value. Maybe 0 indicates some hex value that gonna be the correct code value of for this base code. Anyway, so in this way, we read the line. The line has the value of key and decode it and print out. So read and decode it and print out. So this is the basic way to take the key value from the process interactively, and we can also uh, to read the second value. What is that? The ciphertext, right? So let's get that the same way. We can read P, so read until. So we can put also some conditions that are gonna be the questions. So what is that? Challenge run. So second input is gonna be this question, right? This sentence. So we can put this here, okay, and then read as a cipher text 64. and then decode that cipher. Four, let be 64, decode 64. Okay, and also the print out cipher 64 to the text. And let's print. That's the cipher. Okay, and run again. Yeah, it has the value, right? Cipher base and ciphertext. So how can we get the plain text based on this key and ciphertext? The operation is XOR, right? So I showed the XORing in the last class. So how can we use that? So we can use the for loop. So here for range the length of ciphertext. Okay, okay, and print out match printf print format. Okay, hex cipher each value and another value hex key. Okay, think this is wrong. Okay, so it print out the hex cipher and the key value. Okay, to run out. So you can see they print out the each key and ciphertext. So you just need to XOR these two values that give us the plain text, right? So that is not difficult, maybe. So that is the level two uh, the approach. So secret uh, with one-time path, and we can assume the securely transfer key. But so based on the key value, the exposed key and ciphertext, we can recover the original the plain text. So that was the level two approach. And any questions? The level two. Okay. Let's see one more thing. Level three. Decrypt the secret encrypt with one-time path, the same XORing operation, where the key is reused for arbitrary data. So the similar to the level two, but The level 3, let's see, challenge run. So yeah, they just uh, suggest this ciphertext. Okay, but we need to decrypt uh, the secret key. So we can encrypt arbitrary data with key being used each time. So we can put some data here. Yeah. So the encryption, you have to align the size of the text, ciphertext, and the key size. So here, the key size can be a, multiple of 4, but when you input some other size like 5, yeah, they cannot so encryption. So the multiple of 4 can be encrypted in this mechanism. So in the level 3, we need to interact also the process with the process, right? And like this, we can input some random arbitrary the string, the character, and we can observe the output. So what can be, what is the theory here is we can put some known plain text input, and we can get some the output. So we can compare input and output, and based on that, we can guess some their logic, or how can we discover the key. So that is the in the level 3 concepts. Okay, so here they okay provide key. Okay, so you need use the XOR function on this also, but you have to implement some part uh, like the match and see the result. That is the like some the like the for loop, or try loop. So they can be try and see. So they can have to observe the result. Okay, this case. mm, okay, there is basic concept in the level 3. Okay, let's back to some lectures regarding the symmetric and encryptions, and revisit the module again. So we are now learning about the modern. So in the last class, I just covered some classical, the typical olden cryptography like a CSE cipher. But today, so let's move to modern symmetric encryption. So actually, the this is the classifications of ciphers. So in the classical, so as we see in the Caesar cipher, we usually use the substitutions, right? So how to move the alphabet order, alphabet some the shift value, right? So two step forward or five step backward, like that. Substitutions. That was the initial types of the cryptography, and the transpositions. So the move or byte, some uh, the different order. So there is also the traditional ways to hide some informations in crypt. So modern days, nowadays, we divide that ciphers into two encryptions. The first one is symmetric, the other one asymmetric. So that based on the keys. If the key is symmetric, so we call that the symmetric key. Uh, so the locking and unlocking. So in the symmetric keys, a locking key and unlocking key, those are same. But asymmetric key, the key is different. So they can somebody use his private key and he can give them to the others, and others they can unlock the decrypt with the public key. So the asymmetric key, there's a key pairs, private key and public key. But the symmetric key, there's only one, the same key. So in symmetric key, one of the big issue is how to deliver the same key, right? So if I give the key to somebody, remote, he can be captured or somebody the intercept, the listen, the keys passively. So that is the issues. But anyway, these symmetric keys are very popular in our life. Symmetric key also divided into two ciphers: block ciphers and uh, stream ciphers. So block ciphers, so that's unit of the process. So what size of the unit will be processed? So that is the block. We can say that we can call that the block. So usually the block size is 16 in the cipher. So AES dash 3 dash, they are all use the 16 byte as the block. The stream cipher, the stream is like a byte by byte, the array of byte. So they process each byte, each bit, like the broadcasting the movie or TV. So they encrypt each byte by with the different keys. So this is the very more the practical. In this course, we just only cover the block ciphers. So that is the primary well-known symmetric ciphers proposed by IBM, and the standardized the 1963 or 7. So after some adjustment based on the feedback from NSA, you know the NSA, so intelligence agencies of US, so uh, they would be involved in designing this test cryptography. So we don't know why they and what is the outcome of their involvement. Anyway, so that is very nice at the time. Working with some block of data to encrypt. Okay, but the first key size, the 64-bit data size, so 16 bytes, right? And 56-bit key, that's the length of the key It's like our password length. How many letters in your password? So usually we recommend more than 8 or 10 letters, uh, the mixed by a special character, right? Like that to make the password complex, avoid the breaking or cracking by the hackers. We recommend the more strong and more the longer the password. Like that, the 56-bit key, it is not enough more than this. So this is the basic core net the principles to how to encrypt. Usually, this input text we call the plain text, right? And output is a ciphertext. The text divided in two parts. Let's say left side and right side. So each side is a 32 bit. So the left part directly XORed with some functions, and the right part can be an input the next round. We call that, let's say this is just a one round, and this is a two round, right? So n round. So each round, so uh, each round need the new keys. So here, the sub key. So here actually 64-bit, but it reduced as a 56-bit here, but finally it also reduced to 48-bit in these steps. So here are 32-bit again. So this this input can be 32-bit, 32-bit, and this is the 46 input. Yeah, so unmatch the size, right? So this function, there is some process to match to expand the size of the input. So I will say again, I'll revisit this part. In this way, they are mixed and mixed. Okay, so the 32-bit of the plain text, the half and half mixed and make the last with the sub key. So here sub key 16 sub keys. That means this is the 16 rounds. These 16 keys use the mixed of the plain text, and you can see this is the permutation matrix. So the key will be replaced based on some permutation order. So this is the complex the permutations, and also there is another here is a shift key. So shift operation is also kinds of permutations. So they um shift and make the as a result make the 48 bits. Yeah, half block 32-bit can be XORed with the sub key 48, but as I said, the size is mismatched. So here, how can match that? Use the S box from S1 to S8. Each S box has 6 byte. So six 6 bit, 6 times 8 makes a 48. So this upper block will be expanded to 48 bits, and they are XORed and permit. S box S means substitutions. Substitutions. So based on some specific tables, they are permitted, substituted. the location change, and then yeah, this is the permutations matrix. So S box means here, let's say the input value 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. So here outer bits means 0, 1, right? So here 0, 1, this one, right? And the inner bit 1, 1, 0, 1. So 1, 1, 0, 1. Okay, so it will be 9. Okay, right? So in this way, the um, locations will be changed in the S box. So this is the open data. You can see this table in the Wikipedia easily. Okay, that's the basic operations box. How about this test has some critical um, pitfall. So key size too small. So 56 bits. We can nowadays we have a lot of the great, wonderful hardware power, right? So any our laptops or PC can broke using the brute force attacks. The 56-bit size that is not enough to pre protect of this key. Okay, so 1998, EFF, that is the name of the institutions. They build a custom the ES cracker. Cost is below 250,000. So broke in 2 days the key. And 2009, Copacabana, also they uh, use the FPGA with at a more a low cost below 10,000. So they can also found the key, weak key. So the fall, the DAS is well known to uh, the differential crypto analysis attacks. What is the differential cryptanalysis? So this is the so what is the if you can make the input and some black box print out output, so we can know the input and output. So compare between input and output, and then we can observe some activities or some logics of that black box, and we can guess of the next uh, output. So that is the basic concept of differential cryptanalysis. Also, the DAS is vulnerable to these attacks in 1980s. And linear cryptanalysis, 1996, also contribute to the break these DAS systems. So eventually, DAS withdrawn as a standard. But that was give us a great insight to make the cryptography algorithm, other algorithm. So as alternative, AES suggests so advanced encryption standard. So it is a another name is Legenda. It's standard 2001. The block size is increased from 1 to 8 bit, and there's some three size of the keys: 128, 192, and 256. So DAS has the 56 bit size, right? But DAS increase the key size more than double, triple, and quadruple. So this design, as you can see, sufficient to protect classification information. So for top secret, require the key size 192 and 256 lengths. But implementations intend to protect national security must be certified by NSA prior to their acquisition to use. Yeah, the cryptography is very critical in terms of national safety. So each country they uh, should certify the algorithm in their product produced by any country or foreign country. So like that to give some trust and some guarantee of qualities in terms of the cyber cryptography. There is some uh, the, the governmental agencies like NSA. So we call that DAA. So they uh, certify and verify the crypto algorithm or the related product. Okay. So Intel, yeah, CPU chip company, they also include the AES instructions in their hardware. So that makes uh, the popularity, the more prevalent in in the real world. So AES also in our Wi-Fi or any some authentication algorithm. So AES is yeah the embedded and they protect our informations successfully. So this is the basic AES algorithm. AES is a symmetric algorithm, so only one key are produced. So as you can see, so in the dash, in the dash, so the plain text mix with the key and produce the complex ciphertext, right? So basically, they're the same. AES also mixed, but it has some more different operations. Here you can see add round key and sub bytes, shift rows, and mix columns, add round key again. So here are four operations. Uh, so we will not cover in details of these functions, but basically, uh, so the slide move. Why? Okay. So first operations add round keys. So this we call this the input plain text. We call that state. The state is the byte matrix, 4 by 4. That means 16 byte. Again, the input side is 16 byte in the AES. Okay, so 16 byte. If the text uh, doesn't have 16 byte, how we can do that? Some standard the padding algorithm can be used for compensate that. And 16 byte and also the 16 byte keys, the XORing, right? And that is the change some that makes the output. We call that the add round key. That's just a simple bitwise XOR operations. Second operation substitute bytes. So substitute. This is the substitute tables. So the 00 this is the locations. So 00 will be the 63. So here, so 22, uh, the place will be the new place. So that is the substitutions, and then uh, the shift rows can see the first row is okay, but no change. But second row, they shift left one byte, one byte, one byte, right? And second, uh, actually second row, third row, they jumped two steps, right? So in this way, they shift low. The this is the jump, the three low, three column, actually three the cells, right? So this is shift low. The last one is mixed column. So row mixed and column mixed. So more make them complex, and the each column XOR with some lookup table values. So in this way, they will get a new value. So this is the one round. So they repeat this process based on the specify the rounds. So based on the key, the number of rounds decide. This is the basic operation mechanism in AES. So AES, that's a symmetric uh, algorithm, right? So plain text will be uh, mixed with the keys, and output the ciphertext that is the same, and decryption also using the same key. Then we can get the plain text. So let's outline summarize the ASCII features here. So we call that can call it substitution and permutation network. The key size can be one of these three size, and block size is 1 to 8 bit, the 16 bytes, right? So if the key size 1 to 8, there is a 10 rounds, and key size 192, the 12 rounds. So higher rounds makes more complex of the plain text. So this is the 16 byte key size 16 byte, and it makes 176 bytes. That means there is a 16, there is a 11 sub keys. So these keys be used in the each round. Okay. For example, here we have plain text here, the hello world, and each ASCII has this code value, right? But hello world, it will be just a 13 byte, right? So in this case, thus you can make the output successfully. No problem, no issues in this input. As I can see, as I say, so input should be aligned with the multiple of 16. Uh, that's a rule in the AES. Okay, so we have to add the some path 0000. In this case, it will be uh, the encrypted and output ciphertext successfully, and also decrypted with the same key. But so null byte or here null byte, that is will be ignored, or yeah, ignored in the decryptions. So sometimes they can be mismatched. So in this case, so we use the standard pairing mechanism, pairing scheme PKC number 7. So as you can see here, the padding is changed like a 03033. That means there are three padding bytes, right? 030303. So in the case, because this is the 16 byte, is ciphertext. Also, when decrypted, because that is a standard padding method scheme. Based on that, we can see, oh, the last 3 byte is the padding. So that is the why we use the PKC7 padding. So this is another example how to encrypt. So let's say this two sentence, hello world. So 13 plus 13. So there are 26 bytes, right? How can you encrypt it? But what is the block size? 16 byte. So only these 16 byte will be processed in first encryption, right? And then second, yes, the last uh, 26 minus 16 is a 10, right? This is a size of 10. And how many pad I need? Plus 6, right? So as you can see, can you see? Yeah, so you can see the pad 6, right? So this second block will be processed. So that is the way to encrypt in AES. Okay. In AES, there are three modes to encryptions. First one, ECB, electronic codebook mode, and second one, CBC, cyberblock chaining. Last one, the counter mode. Okay, so what is the difference between them? The first one, ECB. So ECB is very simple, just the input and encrypt with a key and make the output. But as you can see, the key is the same. So if we input the same plain text, the output will be same. That means if we input our specific sum input, that will be make the same output. So this is a very nice to attack the cyber text and find the keys. So that in the level 4 challenge and also level 5. So you have to use this way ECB mode attacks. So basically, this plain text with the same key, they provide some specific pattern. So attacker can identify the pattern and make the some privacy informations. So this is the good example how the ECB mode can reveal some privacy information. So this is the plain text data pattern in the ciphertext. So it can be seen ECB mode is not secure, right? So we cannot get the exact same images, but so we can get some overall images. So what is this? Okay, so that's the so in the real world, the ECB mode is not used anymore. Very vulnerable to figure out or guess. So what is the plain text like that? Okay. So Linux ECB mode allows to figure out the plain text easily by discerning some specific patterns. And a second mode is CBC. So uh, this mechanism doesn't have any randomness, right? So deterministic key make the deterministic output. Very straightforward mechanism. So in the CBC mode, cyberblock chaining, let's give some the randomness in the uh, output, the ciphertext. How can you do that? As you can see, the previous ciphertext will be input to the next encryptions by XORing with the second plain text, second flux. In this way, they give some randomness, right? So we cannot expect it, we cannot predict because, yeah, the plain text may be here A and also here A, but they make the different output. Why? Because the chaining between the round. Make sense? So chaining gives us randomness in a CBC mode. So again, encrypt the penguin with a CBC mode. Yes, as you can see, the pixels encrypt with a random color. So we cannot predict or guess what is the plain text. So CBC mode is more strong to protect the informations. The last one, counter mode, CTR. Uh, the other than this three mode, also other mode is highly developed and used in the real world. Anyway, the last one, the counter mode. So in this case, the plain text, there is some counter here, 0, 1, 2, with a nonce. What's the meaning? So the input plain text will be manipulated, will be changed. So in terms of user, so we input the same text, but the text will be manipulated with nonce and counter. Here, nonce can be the same, but the counter is different, the increase, right? Here, 0, 1, and 2. So this plain text will be different, even we input the same text. So in this way, the plain text will be encrypted with this nonce and encrypt first, and then make the ciphertext. So decryption is a reverse process. So this is the counter mode. Usually, counter mode the it input the blocks, but they make the output as a like some stream. So the AES counter mode are used for some the streaming ciphers. Okay, so that is the difference between these three modes in AES. Okay, so in attacking ECB electronic code book mode, how can we attack? So this is the level 4 and 5. You have to have some background knowledge of them. So in attacking the ECB mode in AES encryption, we have several strategies here. Uh, some exploits. The first one is repeating the patterns. So as we see, EBC mode, yeah, has some specific pattern uh, based on the same input and output, right? So by we can inject some repeating pattern into the plain text. Uh, the pattern can be generated in the ciphertext. The, by doing that, we can reveal the plain text or some keys. about the plain text. Okay, so that's the first way, the repeating pattern identification. So second, interaction with padding. So ECB mode, they do not conceal patterns well. So when how about the padding with some specific the rules like PKS number sevens. So padding allow us to identify that the specific the information like how many padding are involved in that. Like the padding will be the number of padding, right? In the PKS 7. So uh, padding allows us to know the value to be added in the added to the plain text. So that lead us to predict the pattern of the ciphertext in the ciphertext, right? And third one, yes, the prefix control. Actually, in the model 5, if the attacker can the control the prefix or some prepend the data to the plain text, that it can manipulate the structure of plain text to exploit some uh, vulnerabilities in ECB mode. So also in the model 5, you can control the prefix. So the based on how many input the prefix, so the AES they will generate some number of modules. The last one, detecting the pairing failure. So as I see, show you, if I put just a number two or number four, number five, so that makes the failure of the encryption, right? So that is the padding failure. So padding alignment is very important since because the ECB mode they do not handle the padding, so it may result in padding failure as I showed you. So if plain text length is not a multiple of block size like 16 bytes or 4 bytes, so we can see how the decryptions responds to padding failure. So we can distinguish tell the difference between the valid and invalid ciphertext, and we can got some insight what is the underlying mechanism. Okay, so this for the strategy can be helpful to solve the, the module. So let's visit again the module. In the module 4, decrypt, secret encrypted with AES with the ECB mode of operation. So model level 4 and 5, uh, that is the AES ECB mode, very vulnerable mechanism. So we can predict, we can guess some pattern of the output. Anyway, let's run the okay challenge run. Okay, in the challenge you will decrypt secret AES encryptions and ECB block cipher mode. So you used so key and ciphertext. That means we can get the plain text because this is the ECB. Only we can reverse process. So how can we do that? So we can XOR operations with these two factors. So that is the one-time path. But in this case, so how can we decrypt AES? So uh, we should input the the key and the ciphertext into the AES decryptions, right? And then you can get uh, the what is the secret keys. So in this case, I can recommend to use this cyber chef. Uh, Here, they there are AES decryption. Yes, it's decrypt. Okay, so we can input some the ciphertext, right? Input is a key, right? Key value here, and this is the initial vector. So the mode is let's change the ECB mode. So you can try with this. This is ciphertext, right? And this is the key. Ciphertext. So you can put this value in the this lesser p inside the chef. So try to decrypt, but you have to take care. So input format match. So what is the input format? That should be what is the input for the key here? Hex or the base 64, right? Because our challenge is this code everything code encoded with the base 64. So you have to set the base 64 key value and try to input the text key, the ciphertext, and they will show the uh, output some flags or key values. Okay, so that is my recommendations. Or you can also the programming use programming to decrypt the AES key. AES. How can you do that? So AES algorithm is just one of the functions, right? So you can call the library and try to input the key and ciphertext and get some uh, the decrypted keys or the plain text. So that is the solve approach in level 4. Okay, any questions in level 4? Okay, let's move in the level 5. Okay, decrypt secret. So arbitrary data appended the secret, and the key is reused. That means so we need put some arbitrary data the append to the plex here the secret key, and we can compare the input and output what changes. So Okay, let's go to in the level 5. Okay, so there is some announcement. This level is difficult, so check out these lecture videos. I recommend you watch this video to understand the concept of this level. Uh, I just want to show challenges run. Okay, so they show the secret ciphertext and also the hex value of this ciphertext with four module, right? One, two, three, four. So each module gonna be the 16 byte. So that is the how the process in AES for the input plain text. So you have to extract first this ciphertext. Okay, with this is the base 16 format. Okay, you need to convert this 16 format to the hex, and then uh, you need to make some arbitrary data like 4A. Yeah, they make some different modules, right? One, two, three, four modules. So you can increase that uh, arbitrary the plain text prefix. Okay, in this case, uh, you can see the another module is generate, right? So five modules exist. So in this way, it's kind of brute force attacks. So input some arbitrary data uh, uh, as the plain text prefix and observe what changes. So what is the differences between the outputs? So again, that's a basic approach. So try to watch these videos provided by Adam, and the, try, good luck for the module 5. Yeah, it's a very difficult challenges. So any questions so far? Yeah, level 4 and level 5, they are AES ECB mode. So ECB mode has very the critical vulnerabilities. So you can revisit this philosophy, repeating patterns, and interact with the padding, and then what controls we can have. So that's all for today, and see you on Thursday. Thank you.